Welcome to The Explainer. All right, let's just dive right into this. If you're tuning in today, chances are you probably already know your way around a breadboard pretty well. You've blinked some LEDs, read a handful of sensors, and honestly, you've probably built some really cool stuff. But today we're talking about the ultimate level up. We are moving out of the realm of basic microcontrollers and straight into the territory of advanced embedded systems. We're going to look at what actually happens when you take off the training wheels and truly master your hardware.
So let me ask you a question. Are your embedded projects kinda outgrowing your hardware? Have you ever hit that incredibly frustrating ceiling where you're running out of I/O pins, or maybe you're just running out of patience trying to jam everything through a single-lane serial port on a basic board like the Uno? When your code gets complex and your hardware gets hungry, those standard maker boards can suddenly feel very, very small.
Well, that is exactly where the definitive hardware solution comes into play. The Arduino Mega 2560 Rev 3. And listen, this board isn't just an upgrade. It is in a completely different weight class. It's designed specifically as a powerhouse to process the kind of complex algorithms you need for advanced 3D printing, large-scale robotics, and any maker project that really demands serious multitasking.
Let's look at the sheer foundation of this thing. We are talking about an ATmega 2560 processor running at 16 MHz. It boasts a massive 256 kilobytes of flash memory, which means your complex code actually has room to breathe for once. But the real showstopper here? 54 digital input/output pins, 16 analog inputs, and 15 dedicated pulse width modulation or PWM channels. It's literally the hardware equivalent of moving out of a tiny studio apartment and into a massive mansion.
Just take a look at the complete pinout map of the Mega. Go ahead and let yourself be a little overwhelmed, in a good way, of course. You have an incredible number of simultaneous connections at your disposal here. When you've got this much I/O, you don't have to make compromises anymore. You don't have to choose between hooking up a display or a sensor or multiple motors. You just connect them all.
But hey, having the hardware is really only half the battle. To truly level up, we have to break some of the rules of basic coding. Have you ever hooked up a DC motor or a stepper motor using those native PWM commands only to be greeted by that incredibly annoying high-pitched whine? It is a classic maker pain point. And it happens because the native Arduino PWM frequency is set right smack in the middle of our audible hearing range.
To fix this, we're going to bypass the standard commands altogether. Sure, standard commands like analog write are super easy to use, but they are slightly slower and they're stuck at that noisy frequency. However, by using direct register access, we skip the middleman entirely. It's way faster, and most importantly, it allows us to set completely custom, totally inaudible frequencies for our motors.
The crucial trick here is knowing how your board is actually wired under the hood. You need an actionable cheat sheet to see exactly which Arduino pin maps to which timer and counter control register inside the microcontroller. For example, if you want to control pin 2 directly, you don't use analog write, you write a value directly to register OCR3B.
So let's see how this builds into an actual real-world solution. By adjusting the waveform generation mode, specifically by setting it to mode 14 for fast PWM with zero prescaling, we can run at the native 16 MHz clock speed. If we set our input capture register, or ICR4, to a value of 400, the math works out beautifully. 16 MHz divided by 400 gives us a PWM frequency of 47,304 Hz. That is way past human hearing. You get incredibly smooth, completely silent motor control. All right, let's shift gears for a second and look at the physical layout. Think of the Mega 2560 as a multi-lane superhighway routing power and data. You aren't just relying on one chip here. The board uses a dedicated ATmega 16U2 processor specifically to act as an interface for the USB data, effortlessly routing traffic, while the massive ATmega 2560 main processor handles all your actual project logic without even breaking a sweat.
And speaking of data traffic, here's a number that should make any advanced maker smile. 4. The Mega 2560 features 4 dedicated hardware serial ports, or UARTs. On a standard Uno, you get exactly 1, and it's shared with the USB port. But here, you have serial 1, 2, and 3, sitting on dedicated pins, like 19 and 18, or 17 and 16, entirely separate from your main USB communication. Why does this matter?
Well, as our sources point out, the availability of multiple serial ports means that you no longer have to depend on the software serial library. You don't have to sacrifice any digital I/O pins or flash memory. Software serial is a fantastic hack for smaller boards for sure, but it absolutely eats up your CPU cycles and your memory. Hardware serial? It processes the data instantly without taxing your main loop at all.
The practical power of this is just incredible. It means you can hook up a GPS module on Serial 1 and an ESP8266 Wi-Fi module on Serial 2 and run them both simultaneously at full speed. Your project can track its physical location and stream that data over the internet at the exact same time, and the 18MEGA 2560 won't drop a single byte of data or slow down any of your other functions.
And the communication upgrades don't stop there. You've also got dedicated SPI communication pins ready to go right out of the box. That means absolutely no separate library installs to hit those high speeds. Because the SPI library is bundled right with the platform, you can seamlessly connect high-speed peripherals directly to pins 50 through 53 or right onto the ISCSP header.
So what do you do when you have this massive kit of sensors, displays, and modules, and you want to use every single one of them at the exact same time? Standard linear coding, where the board basically waits for one thing to finish before doing the next, it just isn't going to cut it anymore. We need a software paradigm shift to match our new hardware. We need to bend time. We need FreeRTOS, a real-time preemptive operating system. To really prove what this board can do with a real-time OS, let's break down an actual university lab assignment designed for the Mega. Under FreeRTOS, you divide your code into separate independent tasks. Task 1 simply flashes an LED. Simple enough, right? But simultaneously, Task 2 takes over Timer 4 to play the Mario theme song on a speaker. And while all of that's happening, Tasks 3 and 4 are working in the background, performing incredibly complex 512-sample fast Fourier transform math calculations on a random signal.
To make this magic happen without crashing the entire system, the tasks have to be able to talk to each other safely. FreeRTOS uses features like queues for this. Task 3 doesn't just do the math. It uses a command called xQSendToBack to pass a data pointer over to Task 4. Task 4 then uses xQReceive to grab that data, computes the heavy math, measures the actual wall clock time it took, and signals back. All of this data shuffling happens perfectly smoothly in the background while your LED is still blinking and Mario is still playing.
If you can master this, you are officially ready for a stretch goal project. A true advanced embedded system generally meets these criteria. It handles highly reliable timing and I/O. It operates under a high CPU load with tasks running at 50 Hz or faster. It integrates novel external devices you've never even used before. And it features a complex user interface, maybe something like an RFID security system with a keypad entry delay, or a custom-built digital multimeter with a live LCD display.
We've really seen what this board is made of today. From direct register access for totally silent motors to 4 hardware serial ports for massive data flow, all the way up to running a real-time operating system to juggle heavy math and hardware at the exact same time. So I'm going to leave you with this. Now that you have 54 pins, 4 independent serial ports, and a real-time OS right at your fingertips, what is your excuse for not building that absolute dream project? Go grab a Mega 205060 and start building. Thanks for joining me on this explainer. I'll catch you next time.